Welcome everybody. I am Dr. Kamlesh Alti, Associate Professor, Department of Physics, Institute of Science, and I am also affiliated to Physics Department, Santa Gadge Baba, Amravati University. I am lean from this department. Topic of my presentation is teaching methodology for Fourier optics, topic of modern optics. So as you can, as it is there, we have very less portion of optics in BSc as well as MSc. And apart from geometrical optics, learning geometrical optics in the 11th and 12th, there is not much optics left in the BSc to learn. And there is actually very little portion of modern optics which is there in the syllabus. So out of that, the Fourier optics is very important topic, and that's why I chosen the Fourier optics topic today. And this is actually a highly mathematical topic. Fourier optics is a mathematical topic. If you teach this Fourier optics from the mathematical point of view, introduce this Fourier optics from the mathematical point of view to the students, then they will get bored. So I will present to you today a teaching methodology, a innovative teaching methodology for Fourier optics, and let us see how it goes. So what is expected from this talk? I will introduce the topic as I discuss, minus any mathematical jargon. Of course, the mathematical definition I will going to reveal. Then there is a very important connection, and that connection is between the lens, a simple lens uncertainty principle that is in quantum mechanics, and the Fourier transform. This connection I will talk about, and this will actually create a kind of interest among the students when they are learning this topic. I will also discuss the connection, the difference or the comparison between the geometrical optics and the Fourier optics, why Fourier optics is there. And at the last, I will discuss the applications, some of the applications of this Fourier optics. So let us start with this single slit diffraction experiment, which we normally do in maybe 12th level as well as the BSc level also. We can do this simple experiment using a laser pointer, and we can actually make a slit in our home using the blades, razor blades, which we are having. So we can have the slit, we can actually point the laser onto it, and you can see that this diffraction pattern in our home also. So this diffraction pattern, this one-dimensional diffraction pattern look like this. So this is the 1D result. So it is actually having a central maxima, minima, first maxima, and all these things, right? So it is a symmetrical pattern on both the sides. So we will, when we are teaching this in the classroom, we can actually bring this stuff, laser diode as well as the slits, to demonstrate the single slit diffraction pattern. And we will ask students to remember the geometry of the slit as well as the geometry of the diffraction pattern which they are seeing on the screen. Then second, just a minute, so secondly, we take a rectangular slit instead of a one-dimensional slit. We take a rectangular slit, and we will see the diffraction pattern of it in a similar way. In this case, we will get a diffraction, two-dimensional diffraction pattern, right? So diffraction pattern is not only in this direction, but in this direction also. So what we have done here, we are actually increase the sides of the slits. So if by increasing the sides of the slit, we actually getting a 2D diffraction pattern instead of 1D diffraction pattern. So this is what we are getting from the rectangular slit. Then we go on to different geometry, right? We actually having now more sides in this hexagonal slit, which we can make using razor blades also. So when we see the diffraction pattern, each side of this hexagon giving rise to the diffraction pattern in that respective direction, right? So from this kind of demonstration, student will understand that as we are going, we are increasing the sides of the slits, the diffraction pattern also correspondingly changing. Then we will go to the slit, which is having infinite amount of sides. So that is nothing but a pinhole. So pinhole, that is a circle, is having infinite amount of sides. And when we see the diffraction, we will get a diffraction pattern like a concentric rings. So this is all well known. And from here, from this point, from this side onwards, we'll ask the question to the students whether there is a relation between the slit geometry and the diffraction pattern they are seeing. So this is the question that should come up in the classroom. So this demonstration, as I discussed with you earlier, this demonstration can be done in the classroom using laser pointer and the slits made up of razor blades, like is shown in these figures. So the question, the important question which is coming up out of this demonstration is there any mathematical relationship between slit geometry and the diffraction pattern they are seeing? So the answer to this question is yes, there is a mathematical relation between the slit geometry and the diffraction pattern, and this is called as Fourier transform, right? So the Fourier transform is the answer to this question. This is a mathematical relation between them. So mathematically, the Fourier transform look like this, the mathematical definition of it. We always study Fourier transform with respect to the frequency and the time. So when we discuss Fourier transform, we say that by using Fourier transform, we can go from frequency domain to the time domain and the time domain to the frequency domain using these two relationship, which can sum up over all the frequencies and the times which are involved there. So this is the mathematical definition. Next slide. So this is actually after learning that there is a single slit diffraction, double slit diffraction, the rectangular slit diffraction, hexagonal slit diffraction, pinhole diffraction. So there is a relationship between the diffraction pattern and the slit geometry, and that is nothing but a Fourier transform. So this is just an application of the Fourier transform directly they are seeing, the students are seeing. Now the next thing is whether there is a connection between the quantum mechanics, simple geometrical optics, the lens, the geometrical optical component, that is a lens, and of course the laser, which is the part of quantum electronics, with the Fourier transform. So whether there is a connection, we will probe next this connection, and this will actually student will get more confused why we are learning all these things, right? About what is the connection between the Fourier Fourier transform and the uncertainty principle, the laser and the lens. But there is a connection, and when they will understand the connection, they will appreciate the Fourier optics more. So let us do that. This is a simple lens, and as you can see, what simple lens can do, it can actually, if you have a collimated light rays, it can actually focus this light rays, and when you have a point source, and if you shine the point source onto the lens, right, with the distance between the point source and the lens equal to the focal length, then it can convert it to the collimated rays. So this is what they are learning maybe 11th or 12th school level physics. Now I will actually describe this process in a different way, right? So imagine the collimated rays, which are actually the input for this first one, is can be called as a constant function, right? So this is the constant function. This looks like a constant function, and when they are actually falling onto the lens, they are getting focus onto one point, right? So this one point, the light exists, and at other points, right, at this zone, the light do not exist. So this actually corresponding to a direct delta function, which is there in the quantum mechanics, which we are learning in quantum. Of course, this is a mathematics, but we are learning it in quantum mechanics in MSc or in BSc also. So this is nothing but a Dirac delta function, definition of Dirac delta function. So at one point, the function is shooting up, and at all the other points, the function is zero. So this is the definition of Dirac delta function. So what this lens is doing now is it's actually converting a constant function into a Dirac delta function, and it can actually do the reverse, right? So if you have a point source represent a Dirac delta function here, and it can convert using the same lens this point source into a constant function. So this is what the lens is doing, right? So I have just explained it in a different way, right? You involving the constant function as well as the Dirac delta function. Now next one is the uncertainty principle. So I'm not actually talking about the uncertainty principle or between the delta x and the delta p, that is the coordinate and the momentum. So I'm talking about the delta nu and delta t. So delta nu is the frequency and delta t is the uncertainty in the time, and this is the uncertainty in the frequency. So frequency and time, between the frequency and time, this is the uncertainty principle, right? So let us actually talk about this, right? This delta nu delta t is equal to 1. This we can derive easily from delta E delta nu equal to h, right? And we can convert that E is equal to h nu. From that we can actually derive this delta nu delta t equal to 1, and this is also the one of the form of the uncertainty principle between the frequency and the time. Now let us actually try to learn from this principle and see how it is connecting to the previous example of the lens which we have seen. Now take the example of monochromatic continuous wave laser, right? So as you see, as you know that the laser is having a property, and the property is it is having only one single wavelength, right? Single wavelength means single frequency. So if it is having a single frequency, if you draw a graph between the intensity versus the frequency, right? As you can see here, you will see that only at one particular frequency the graph is shooting up, and at all the other frequencies the graph is the intensity is zero. So only at one frequency the intensity is high, and at all other points the intensity is zero. So this is nothing but the definition of derived delta function. So this is what it has come up now, right? So derived delta function. So now this is for monochromatic continuous wave laser, and from here from the time domain, right? This is the frequency domain. If you go to the time domain, when you see the time domain, when we switch on the laser, right, at one particular time, and we will not disturb the laser, so it will actually give the intensity continuously, right? So it will give the intensity continuously. That means you'll get a constant function, right? So as the time progresses, you will get a constant intensity from the laser. So we can actually plot a graph between the time and the intensity, as we have plot plotted frequency versus intensity graph, and you will see a constant function. So this is the what we are, it is happening in the time domain. So if you put this, right, so when this will stop, this will never stop, this will actually this is a continuous function, constant continuous function, and it will never stop. As long as the electricity is there, the laser will never stop. And this is the time you can actually insert in the uncertainty principle as infinity. So if you put that there and calculate what is delta nu comes out to be 0 using this uncertainty principle. And this is what exactly it is happening, that at one particular frequency, this graph is shooting up and it is having a width 0, right? So there is no width to this line and it is 0. So this is actually predicted by the uncertainty principle already. So time domain is a constant function, and when you go to the frequency domain, it's a Dirac delta function. So it is very similar to the previous case. In the lens, we are also seeing that is a constant function, and when we do the reverse, it's a delta function. So this is actually, in the previous slide also, we have seen that the lens is doing this constant function to the Dirac delta function, or Dirac delta function to the constant function. And in this case, the laser, right, which we are using nowadays everywhere, now there also we can see the similar thing. So what is the connection? The connection is the Fourier transform. So if you do the Fourier transform of the constant function, you will get actually a Dirac delta function, right? When you study the Fourier transform mathematically, you will actually study you will study the lot of functions there, and how to do Fourier transform on that functions. So if you one of the function is a constant function or the Dirac delta function, so if you do the Fourier transform of that, you will get a Dirac delta function, or if you do the reverse, you will get a constant function. So the answer is actually the Fourier transform, right? The connection between them is a Fourier transform. So not only we have seen that this is there in the uncertainty principle, but there is also a simple lens which can actually demonstrate the Fourier transform. So what we have learned from this is everything is connected, right? So the topic which is very much different, as you can actually see from this slide, right, that the quantum optics topic and the quantum mechanical topic, right, geometrical optic topic, right, and the Fourier optics topic, which are actually very different, right? And the students understand that they are different, they are not having any connection, they are actually now connected with each other. And students at this point, they will appreciate that there is a connection, and we are not actually look into the topic of this Fourier optics in this way. So they have actually learned only the mathematical jargons first, and they have converted some functions and taken their Fourier transform, and they have seen that how their Fourier transforms are behaving, but never this connection has been revealed in the classroom. So everything is connected. So connection is actually a reciprocal relations, right? So we can see that everywhere there is a reciprocal relations which are there in the lens, also in the uncertainty principle. Also, when we calculate that delta nu, it's 1 by infinity, that gives a 0. So this is the reciprocal relations which are actually the connections between these two. So this is not only we have seen here in this lens and uncertainty principle, but we are actually seeing and using it in the X-ray diffraction. So whenever we are actually taking the X-ray diffraction, we are actually using a Fourier optics there. So we are actually going from the real space to the reciprocal space, and we get when we actually getting the X-ray diffraction pattern, we actually getting a pattern in the reciprocal space, which we can interpret back and using Fourier transform and can get the information about the unit cell crystal structure of that particular sample which we are using. So when we actually study this X-ray diffraction topic, we study this in the solid state physics. But when we study this in the solid state physics, students feel students actually are actually missing this point, that this is not a topic of the solid state physics. It's a topic of modern optics. This is a topic of Fourier optics, and the main term, the important term, the Fourier optics, is actually missing from all the standard kind of references which the students are been using, and also it is not been discussed in the classroom. So this is actually this kind of connection between the topic which is there in the solid state physics, the student should understand. And this is not actually a topic of solid state physics, it's a topic of the Fourier optics, right? And this is very important thing, that they should able to correlate this with the Fourier transform. So when the X-ray diffraction has been first started, the reciprocal space diffraction pattern which people they have been getting there, they have transformed this reciprocal space diagrams into the real space diagrams, direct space diagrams, and they got information about the crystal structure. And there everything was documented properly, literature was there. So nowadays we are just taking the X-ray diffraction pattern and then matching it with the literature which is there in the files, reference files. And when the things are been matching, the peaks are been matching, we say that okay, this is the crystal structure. We are actually taking a shortcut here. We are not been calculating anything using the Fourier transform nowadays, because the literature is available. But this is the proper procedure, and students should understand that this is the topic of Fourier optics. So X-ray diffraction also is the connection. So what is the difference? Why we actually been stressing more on the Fourier optics in the modern optics era? So the thing is, when we actually comparing with the ray optics, ray diagrams reveal only trajectories of light beams to determine imaging characteristics such as location of image and image magnification. So complete description here requires monitoring of wave properties of light, such as phase of propagating beam. So phase is very much important parameter which we have been missing out in all these things. Even when we are actually taking a simple picture using a camera, when we see the photograph, we actually seeing only the intensity of light which has been changing from pixel to pixel, but we actually never calculated or never appreciated that there is a phase which is also been changing, and we actually there is no actually direct technique to determine the phase of the light beams using just an image. But this is there. The phase is also very important parameter, and in fact, this is the only important parameter which is there, the phase. So phase, how the phase is changing when it is actually going from one lens, or it is from bouncing off from mirror, or it's been getting a dispersion inside a prism or the other diffractive optical elements. So how the phase is changing, we are never calculating using a ray optics or geometrical optics, but this Fourier optics give us a mathematical way to calculate the phase of the propagating light beams. So Fourier optics is one possible wave treatment which is which considers the Fourier spectrum, the space of spatial frequencies of the object, and the transmission of the spectral components through the optical system. So this is the difference between the Fourier optics and the ray optics. We are actually stressing more on the phase of the light beam. Sorry. So what are the applications of the Fourier optics? So one of the application we already have been discussing, that is the X-ray diffraction analysis for studying crystal structure. But there are some other methods also that, like, we actually understand the imaging system more. As we are actually calculating the phase, we will understand that how the phase has been varying as the light is passing from one medium to the another medium. And if we can control the phase, we can control many things in optics. So understanding the imaging system more with the Fourier optics, we can actually test various optical components using the Fourier optical analysis. So if there are some defects, minute defects inside the optical component, and due to that, if there is a variation in the phase, we can actually calculate that phase using the Fourier optical analysis. So the laser shows which we have been actually seeing in all the major inauguration programs, whether there is a IPL or cricket World Cup or any other tournaments. The laser shows, in the laser shows, we can actually see that there are some 3D models which are appearing in the air. So how they are doing it? They are actually doing it with the help of a diffraction, right? This another application of the diffraction, which actually we had discussed earlier in the slides. So if you can change, if you want one image to appear on the in the air, you can actually take the Fourier transform, inverse Fourier transform of that image, and can actually get the slit accordingly, right? Slit accordingly, we can cut it, and if we can insert that slit in front, if we keep the slit in front of the laser, we can actually see the image, respective image. So this is nothing but a Fourier transform, which we have already seen in the earlier slides. So laser in the laser shows we actually using the Fourier optics. Many image processing application, the Fourier optics has been used, the fast Fourier transform, right? It has been used for getting the phase information as well as clearing the noise from the image. We actually been using the Fourier optics. There is another very interesting application that is called as a holographic. So holographic sticker, we already know what is a holographic stickers, and many of us having the laptops on the laptops, the Intel sticker is there, and when you see that from some certain angle, like you can actually see some certain 3D effects, 3D image inside that sticker. So it is actually nothing but a holographic sticker which actually they are been placing there, and there is no way we can actually copy this sticker, right? So this sticker cannot be copied. We cannot take a Xerox copy of that sticker and stick it. So this is very unique because the phase information is been hidden there, right? And the phase information is unique to that sticker. So if you want to create a copy of that, you need to create the same setup which they are having, holographic setup, and it is not possible to create the same setup because the phase variation, minute phase variation will be always there. So holography, the Fourier optics has been used. Then the optical communication, right? In the optical communication also, they have been using the Fourier optics when we transform our video as well as the audio from one part of the city to another part of the city, or maybe across the continent. Then it is actually going via optical fiber, right? It has been transformed from electrical domain to the light domain, and the light is been traveling along the way. So all the modulations, demodulation which have been happening there, somewhere we actually been using the Fourier optics there for Fourier transforms. We've been used there for the conversion from one domain to the another domain and clearing out the noise from the signal. So there are actually many more applications of the Fourier optics. These are just a few applications which have come to my mind, and there are of course the many more interesting and the innovative application which maybe student can actually reveal. They can do more experiments, more research on that. So these are the applications of the Fourier optics. So these are some of the references. This is one of the very good book which I figure out, which is very good for the Fourier optics. The first few chapters of this book, Elements of Photonics Volume 2 for Fiber and Integrated Optics by Izuka, is actually a very good book on this topic. For slide number 17, actually I use the data which is been there in this website. So this is the references for the PPT. So this is the end of my talk. Thank you for listening, and I hope this entire slides from 1 to 21 has given you some idea about how to introduce the Fourier optics topic to the students. And of course, when I introduce this Fourier optics topic in my classroom in this way, the students they actually appreciated more about the topic, and they have said that they actually very much got interested when they have heard the connection between the Fourier optics and all the other subjects, which earlier they have thought that they are different and there is no connection between the optics and maybe the quantum mechanics or the X-ray diffraction. So thank you for listening.